Hi, welcome. This is the second part of the recap from Sunday. I'm sorry it took me so long. We had a number of technical problems, and so I was able to copy and paste those PDF files that I shared on Blackboard into PowerPoint slides, and I'm recording it using PowerPoint, and I'll download this to YouTube. This will be very informal, just a recap of how odds ratios and risk ratios relate to the decision between a case control versus a longitudinal studies design. So this week we're transitioning into the concept of study designs, and you have gone through the ethics review, or you're completing the ethics certification process. So think about whether or not you have a disease that's suitable for measuring over a long period of time in an observational study, or whether you want to do a cross-sectional study. By now you will have sorted through or thought about the ethical issues with a randomized controlled trial, or sometimes known as a randomized clinical trial. With a randomized clinical trial, you're talking about a longitudinal design, and it would be measured either in terms of risk ratios or rate ratios, which are the same measures we use for observational longitudinal studies as well. And these will be compared in this next slide to odds ratios conceptually. And particularly, I want you to think about why and how an odds ratio is a good estimate for a rare disease. So I'm going to go through an example where I demonstrate a comparison. So looking at the worksheet will help you. This is really just a recap of that worksheet, but putting it in the context of study designs. And then the second slide is just that same whiteboard that we went through on Sunday, which is also about the concept of rate ratios, but it's really specifically about the concept of what is person time and how is it assessed, because this is a question I often get. Should we measure people over time, and should we measure person time in that equation, or just use risk ratios? So we're going to start with odds ratios versus risk ratios, and then we're going to move on from there onto the concept of rate ratios and person time. Okay, so here we have two sets of 2x2 tables. On the left side, I'm looking at measles versus no measles to give you an example of a rare disease scenario. And on the right side is a 2x2 table where we're looking at a more common disease, and I'm giving the example of the flu. Now, these numbers are all just made up to illustrate the example that in a rare disease scenario, your odds ratio is going to be pretty much the same as your risk ratio. So rounding up, the odds ratio is 2. The risk ratio is also 2. And when you're looking at a common disease, the odds ratio can be very different from the risk ratio. Here I'm going to give, just to illustrate the example, imagine you have a school where most of the kids are unvaccinated. So in the measles example, imagine you have the kids are unvaccinated, and then you're comparing them to schools where most of the kids are vaccinated. It's not unrealistic to imagine in that scenario you would have more measles in the school with unvaccinated children. So imagine that that's the row we're talking about. So if the disease is rare, the odds ratio is going to look like this. It's going to be 50 divided by 9,950, and then that would be divided over 25 divided by 9,975. Now imagine you replace that B, that's how the odds ratio formula works, with the sample size, the total sample size of 10,000. It's not going to make much difference. So mathematically, your odds ratio and your risk ratio are going to be virtually identical when you have a rare disease scenario. So this is just to give you some numbers to get a sense of why the rare disease scenario works. I'm also showing this formula so that you just remember when you're looking at an odds ratio, we often in epidemiology think in terms of the A, B, C, and D quadrants. So I've labeled these so you can see that the exposed and diseased conditions will always be in the A quadrant, and the non-exposed, the non-diseased condition, so look for the second column in the second row, is going to be the D condition. And when we do the formula of 50 over 9,950, imagine A divided by B, which is then divided by C divided by D. So when we write out the formula, often we just use the cross-multiplied shorthand version, which is A times D over B times C. So just think about that so you can remember the odds ratio as a formula. It's something that will carry through all of the courses that you take in classes in public health when we're referring back to odds ratios and risk ratios. Know what's behind that formula and how it works. So on the left side, you have a condition where if you replace 9,950 with a total sample size of 10,000, it doesn't really make much difference because not too many people are taken out of that original n. So B is roughly equivalent to the total sample size for the non-vaccinated schools, and then D is roughly equivalent to the total sample size in the kids who are coming from schools that are vaccinated. So I haven't labeled, usually I would label those rows. I haven't labeled it, but I'm just telling you, imagine that's the scenario. So in the worksheet, you'll see all of the labels. And if you look to the right, it really makes a huge difference whether or not it's a common disease. So you can see that if 50 kids get the flu, only 50 kids are left without the flu. So that number of 50 cannot be replaced with that sample size of 100. Those are really different numbers and they say different things. So when you're looking at the common disease scenario, the formula, you can't simply replace the B number with the total sample size without taking information away. So the odds ratio is really good for calculating risk when you have a rare disease, but it's not as appropriate for a common disease. The same thing is true when you're looking for study designs. If you think in terms of a study design, if you have a really rare disease, it doesn't make sense to measure it in a longitudinal type of study that you would measure over time because it would take a really long time and a lot of people to sample before you could get the information that you need. So because odds ratio theoretically works best in a rare disease scenario, when you do a study that's a cross-sectional study and you compare, for example, cases to controls, you get a better estimate of a risk ratio when what you're looking at, the case condition, is a rare disease. So this is sort of a mathematical explanation for a rare disease scenario, which is something where a cross-sectional study design or a case control study design works better. And then the analysis that you would do would be in the form of an odds ratio. When you have a more common disease, it occurs more often, you wouldn't need as long, usually you wouldn't need as long of a time period to follow people, depending on when you say if it's a common disease, how long does it take to get that disease? So if you're thinking in terms of a longitudinal study, how long would you have to measure people before they get the flu, for example? It wouldn't take very long for people to get the flu. You can measure a lot of people, a lot of cases, especially if you go in during the flu season, over a short period of time. So it makes sense to do a longitudinal observational cohort study. You could do that over a period of 3 to 4 months and capture a number of cases of the flu. Just keep in mind, if the disease is common, you'll have a situation like what you have on the right, and you might still decide to do a cross-sectional study for different reasons. So think about, does a cross-sectional study make sense? How challenging is it to do a longitudinal study, even if it is a common disease? Do you have the resources available? Are there ethical concerns? So sometimes you'll make a decision to do a cross-sectional study and do an association, maybe even a case control study where you have to do an odds ratio analysis. And if that disease is common, just be aware that your odds ratio will be artificially inflated over what it would be if you had measured it in a longitudinal study. Now, this is a simplistic view I'm giving you. This is a simple mathematical formulations. There are other ways that you can work around your study design. Those are higher level concepts we'll get to in further courses, probably in biostatistics or maybe even a little bit later in the semester. But the rare disease is the first thing you should think of when you think of whether you do a case control or cross-sectional type of study design, either one, as compared to a longitudinal type of study design, whether that's an observational study or a clinical trial. And just to be aware that if you were to flip around the exposure conditions, so this is something I demonstrate in the worksheet, if you were to take the row that reflects C and D and have that be your exposure group, and if you were to have the 25 and 75 be your exposure group, then you would see something that's a protective effect. So let's say instead of comparing the unvaccinated schools to the vaccinated schools where the risk or the odds ratio is 2 to 1, so they're double the risk, if instead you're saying I want to look at the schools where most of the kids have been vaccinated, well, they have half the risk. And then if you compare on the right side with the flu, they have a third the odds ratio or the odds, or with a risk ratio, half the risk. So this is a way to look at analysis. Just remember that, if you just flip your exposed and unexposed around, it's going to change your numbers. It will be the inverse relationship, roughly. Sometimes with an odds ratio that can change a little bit. But just be aware that the tables and the ratio measures are flipped. So you can see that illustrated in the worksheet. The second point I wanted to make, one of the questions I often get from students is what is this concept of person time? So this graphic is really just to illustrate the concept of person time because it relates to the concept of risk ratio versus rate ratio. So here I just wanted to give a scenario, simple scenario. Let's say you have a group of people who are 30 or 40 years old and you're studying them for over a period of 40 years. And the longer you carry out a study, the more likely it is that the condition you're looking for is going to occur. So in this case, we're going to say on the left side you have smokers who are exposed to asbestos, so that's our exposure group. On the right side are smokers who are not exposed to asbestos. So the asbestos is the exposure difference between these two groups. And in both of these cases, left side and right side, the risk ratio would be exactly 1.0. Because in both cases, 4 out of the 10, so the 4 lines in red represent the 4 who did not survive the whole study period, and the 6 black lines represent the 6 people who did. So if you had 10 and 10 on both sides, and on both sides you had 4 people who didn't make it through the whole study period, you would have 4 out of 10 in both groups that died, and you would have a risk ratio of exactly 1. Now, if you look at the same example in terms of incidence rate, you would get a slightly different answer. And I'm just, there's some cross out of the incidence rate ratio that I gave on the initial slide in the PDF. So just be aware that the real answer should be 1.12. We'll get to that. But when you calculate the incidence rate in the exposed, so say the left side, the number 4 is the same on the left and the right side. So your 4 cases over the time frame, you start with unexposed, people who are living, and over the 40-year time frame, 4 died. That number 4 is going to be the same in the exposed and the unexposed group, the left side and the right side. The difference between the left and the right is not the number of people who died or didn't die, it's the amount of person time they contributed. So when you're looking at incidence rate, you're looking at how many people got the disease divided over the total person time of the whole population. That includes those who did get the condition, or in this case, the outcome of death, versus those who survived the entire period. So everyone who survived, the 6 people who survived the entire 40 years, each person is contributing 40 years, so 40 times 6 is the 240. So you have 4 divided by, and then that plus 240 is the same. The difference between these groups is the person time contributed by the people who did not make it through the total time frame. And so on the left side, they only lived for 20 years each. So 20 times 4 is 80. So the exposed group, their incidence rate is 4 cases over 320 total person years. And so that comes out to be, and so if you look to the right, it's 0.0125 deaths per person year. So basically, it's a concept of averaging out how many deaths happened over the total time period being measured. Not just the 40 years, but the total person time being measured. The denominator here is how many people died in the unexposed group over the total person time contributed there. And because people survived longer, that 80 number doesn't hold up. It's 30 years for each person that didn't make it through. So they survived longer, but they didn't survive the entire period. So in the unexposed group, you have 4 people who died divided over the 120 years, that's that 30 years each with 4 people who died, 120 person years that they contributed, plus the 240 person years contributed in total by the people who made it through the whole time frame. So the final result is that 0.0125 deaths per person year in the exposed divided over 0.011111 deaths per person year in the unexposed group. So the incidence rate ratio, dividing these two out, is 1.12 times more instances of death per person year. So essentially what we're seeing is on the left side, they're dying at a slightly faster rate. So when we look at rate ratios, we're not just looking at the concept of did they get the condition or not, but we're looking at how quickly did they get the condition. And so this is the kind of analysis you might do if you're looking at something where it's not just about whether people get the condition, but you're also interested in how quickly do they get the condition. Then we talk in terms of a rate ratio, and you might be interested in measuring person time and assessing incident rate ratio when you're looking at the outcome if you're doing a longitudinal study or measuring people over time. Okay, thank you very much. I hope that this helps to clarify some of the points and makes you think about how you look at your study design for your study design project that you're already starting on but isn't due until next week. Thank you.